My name is Mandelbaum, and in this video I'm going to introduce the concept of endomorphisms of linear block codes. This is a talk I presented at this year's ISIT. I will start with a short introduction in which I will motivate this work. Then I'm going to introduce the concept of endomorphisms of linear block codes and showcase endomorphism ensemble decoding as a possible application of endomorphism. Then I will finalize with a short conclusion. I want to start with a short motivation. It is known that the automorphism group of codes has been successfully used in different areas of coding theory. For example, they have been used in the proof that read-Muller codes achieve the capacity on the erasure channel, also in enumerating minimum weight code words of polar codes, and they are also used in ensemble decoding schemes, where they are used to generate diversity at the receiver side to then improve decoding. This motivates us to analyze other structural properties of codes, namely endomorphism. Now I want to introduce the concept of endomorphisms and distinguish them from automorphisms. To this end, I will first start by introducing the notion of the automorphism. In classical coding theory, for example in the book by McWilliam and Sloan, the automorphism group of a code is defined as follows. Hereby, the automorphism group of a linear code is defined as the set of mappings pi A, which map the code space again onto the code space. Pi A are what I call scale permutations, because pi is an element of the symmetric group, therefore it is a permutation, and A is some non-zero element of our finite field, and pi A is then applied where we permute x according to pi and then scale it with A, therefore the naming scale permutation. And now the automorphism group consists of all scale permutations that map the code space again onto the code space. This makes sense from some structural properties of the code, because with a scale permutation you will always map a code word of a certain weight onto a code word of the same weight. However, in a recent work, we introduced the concept of the generalized automorphism group. Hereby, the generalized automorphism group of a code consists of all linear bijective self-mappings. Therefore, in contrast to the first definition, we drop the necessity for having a scale permutation, but we consider arbitrary linear bijective self-mappings. Therefore, in this case, we do not guarantee anymore that code words of same Hamming weight are mapped onto each other. However, we showed in our work that this generalized automorphism group can also be used to improve decoding at the receiver side. It is interesting to highlight that all linear mappings can be represented by multiplication with a transformation matrix, which we will use in the remainder of this presentation. Now I want to define endomorphisms of linear block codes. We say that the set of endomorphisms of a code consists of all following linear self-mappings, as defined as here. Therefore, all linear mappings that map the code space again onto the code space. Therefore, in contrast to the generalized automorphism group, we drop the necessity for being bijective. Furthermore, we denote by TE the set of transformation matrices of endomorphism. Now, with this picture, I want to illustrate a bit the difference between automorphisms and endomorphisms. Automorphisms are bijective, therefore they perform a one-to-one mapping. Here we have a cloud, which represent our code space, and black dots are code words. If we have an automorphism, we have a one-to-one mapping. Therefore, one black dot is again mapped onto another one black dot. However, if we have endomorphisms, we can have a case as depicted here, where possibly multiple black dots are mapped onto the same black dot, because we drop the necessity for being bijective. Therefore, it also makes sense now to define so-called equivalence classes, which consist of all code words that are mapped onto the same code word by our endomorphism T or tau. We will denote these equivalence classes by those brackets, and K of tau hereby denotes the kernel of our endomorphism tau, and as I introduced before, a capital T denotes the transformation matrix, in this case, of our endomorphism tau. It is known from the first isomorphism theorem that the set of all equivalence classes themselves form a vector space, noted as follows. And this vector space is typically named Gaussian space. Now we want to derive or propose some structural properties of transformation matrices of endomorphism. And to this end, I'm going to walk you through some steps towards theorem 1, which will provide such insights into their structure. To this end, we consider an arbitrary linear code C, which is defined as the kernel of a parity check matrix or of its parity check matrix H, which, for simplicity, we assume to be of full rank. Now, linear self-mapping T maps C onto an image of tau. Now, we want that if we apply T to X, we are still in the null space of our parity check matrix H, because then we map the code word again onto a code word. Therefore, our objective is to find all mappings tau such that the image of tau is a subset of our kernel of H. Therefore, if we have an equality here, so if the image of tau equals the kernel of our parity check matrix, we have a generalized automorphism. However, if we have a proper subset, we have an endomorphism that is not bijective. And now we will use a similar approach to our previous work, where we transform our parity check matrix by Gaussian elimination into the following form, which we denote by H tilde. Here, to perform this Gaussian elimination, we multiply our parity check matrix by the right-hand side with a code characterization matrix A, which is non-singular, and then we obtain a matrix H tilde, which possesses an identity matrix on the left-hand side and a all zero block on the right-hand side. Because H is full rank, we can always perform such a Gaussian elimination. And the benefit of doing this transformation is that the code defined by H tilde is very easy to be described, because it consists of all canonical unit vectors with non-zero entries in the last k positions. And now the set of endomorphisms of the kernel of H tilde, therefore of the code which has this simple to describe basis, consists of all matrices within this set. Therefore, we will take a closer look now. The set consists of all matrices set that have the following form. They have an arbitrary matrix C, D, and E, and an all zero block in the upper right corner. And all those matrices form endomorphisms of the code defined by H tilde. And now, by performing a conjugation with the code characterization matrix, we can identify all transformation matrices of endomorphisms of our original code. Therefore, matrix T is a transformation matrix of an endomorphism if and only if we can find a set in this following set such that T is obtained by conjugation with our code characterization. Furthermore, we can now define something we call rank deficiency, which is denoted by S, which can be used to describe the cardinality of our equivalence classes. And from the proof, it follows that this rank deficiency is simply k minus the rank of. Next, I want to introduce some additional structural properties of endomorphisms, namely that the transformation matrices themselves, the set of transformation matrices, form a vector space. To this end, we define a mapping vectorize, which stacks the columns of a matrix one large column vector. Obviously, this is a one-to-one mapping, and we can define an inverse mapping. Now, I introduce proposition 1. We consider a linear code C with dimension n and k. Then there exists a linear code CE of some larger dimension, so larger Proc size n squared, and some dimension 2 times kn minus k squared, such that all code words from this larger code, if we apply the inverse vectorize operator, yield the transformation matrix of an endomorphism of our code C. Therefore, the set of vectorized transformation matrices of endomorphisms form a linear code. There exists a lot of algorithms to search for certain code words. And now, because we can describe the transformation matrices as code words of a linear code, we can use those algorithms to search for teeth with some properties, for example, sparse teeth. Next, I want to introduce another proposition that can be used to construct the transformation matrix of endomorphisms based on the knowledge of the automorphism. To this end, we consider a linear code with two automorphisms tau1 and tau2 with transformation matrices t1 and t2 respectively. Then the superposition, therefore t equals t1 plus t2, yields the transformation matrix of an endomorphism. Therefore, if we have knowledge of the automorphism group, we can construct T1, T2, and then obtain the transformation matrix of an endomorphism. Let me show you some examples. We know that the we have a lot of knowledge about the automorphism group of the extended Golang code and the 5G polar code. For example, it is known that the automorphism group of the 5G polar code contains the lower triangular affine group, and the automorphism group of the extended Golang code is the Mathieu group N24. Now, we can sample some automorphisms either from the LTA group, generate the transformation matrix, superpose them, yielding an endomorphism of the 5G polar code. Now, as we shown, we have a simple way to obtain the transformation matrix of endomorphism. Next, we are interested in the so-called reconstruction matrix, which maps an element of the image of our endomorphism onto a single representative of our equivalence class. I want to illustrate this again with the picture we know from the beginning. Here we have on the right-hand side the image of tau, which consists of all code words we obtain after applying the endomorphism. And now, if we multiply any of those code words with our reconstruction matrix R, we want to find one of those red dots on the left-hand side, which is member of the equivalence class, which is mapped onto a code word on the right-hand side. And we are able to provide theorem 2, First, it is known from the first isomorphism theory that there exists a bijective mapping ρ, which maps from the image of tau onto the quotient space with the transformation matrix R. And what we now further showed is that R must be of the following form. So it's also conjugated to the code characterization matrix, and set R is of this in the set that we defined previously. And then if we multiply any element of the image of tau with R from the left hand side, we will obtain an element of the equivalence class as depicted here. And in our paper, we provide an algorithm to determine set R and therefore how to construct a reconstruction matrix R. And furthermore, we provide an algorithm to obtain the kernel of tau. And now, given one representative of our equivalence class and the kernel of tau, we can reconstruct the whole equivalence class. Okay, x tau that was denoted here. Now, I want to introduce endomorphism ensemble decoding as a possible application for endomorphisms. Endomorphism ensemble decoding can be described by the following block diagram. It consists of k parallel paths. At the input, we have a received word y, which can be, for example, the output of a binary input AWGN channel. It consists in each path of a pre-processing block, a decoding block, and a post-processing block. And in the end, the outputs of all paths are combined in a maximum likelihood in the list, ML in the list block, which then outputs the final estimate. Let's consider it one single path. We obtain y, and y is then pre-processed to mimic the effect of a linear mapping, for example, of an endomorphism T at a receiver site in the LLR domain. We already introduced this pre-processing in our previous work, where we used it to pre-process according to a generalized automorphism. However, this can also be used for an arbitrary linear mapping and therefore also for an endomorphism. This yields us at the output in vector of log likelihood ratios denoted by L tau I. Now it is known that the decoding success depends on the noise representation at its input. And now, because we have k different LLR representations at the decoding input, we can obtain possibly k different estimates after decoding. However, those estimates are now in the domain or in the code space defined by the image of, in the subcode defined by the image of tau. Therefore, we must use a post-processing to map the estimate onto its corresponding equivalence class, therefore onto all code words that would be mapped onto this estimate when we apply our endomorphism. This is done by this post-processing block here highlighted in gray. Therefore, for each pass, we obtain q to the power s estimates, therefore one equivalence set of code words that would all be mapped onto the same estimate. And then, using the ML in the list operator, we can choose the best estimate among all path candidates to obtain our final estimate. It is nice to highlight that EED incorporates automorphism ensemble decoding, generalized automorphism ensemble decoding, and also multiple basis belief propagation decoding. And the decoding, the block in the middle, can be an arbitrary decoding, such as successive cancellation decoding if we consider polar codes, or the belief propagation decoding if we want to decode an LDPC code. Now I want to show you some simulation results. First, for the extended GoLi code. As I showed you before in an example, we can obtain transformation matrices T of endomorphism of the Golang code using this superposition proposition, where we first use the knowledge of the Mathieu group to generate transformation matrices of our automorphism, and then by superposition we obtain transformation matrices of our endomorphism of our Golang code. Here I depict the frame error rate over the B over N0, and as a baseline decoders, in black we have the performance of maximum likelihood decoding, in orange we have the performance of multiple basis belief propagation decoding using 4 parallel paths, and in blue we have the performance of belief propagation decoding. And now in green we have the performance of endomorphism ensemble decoding, where we use 4 parallel paths and within each path belief propagation decoding. And as we can see here, we are able to improve the performance compared to MBBP, in particular in the lower SNR regime, and at higher SNR we obtain the same frame error rate. Next, I want to show the performance, the simulation performance for the 5G polar code. Again, we have on the y-axis the frame error rate, and on the x-axis the B over N0. And here we depict the performance of maximum likelihood decoding, and as additional baselines, the performance of successive constellation decoding. And it's very interesting to highlight that it is known that for this particular 5G polar code, the automorphism group cannot be used to improve decoding. Therefore, the performance of successive cancellation decoding and automorphism ensemble decoding using successive cancellation and some automorphisms of the linear lower triangular affine group cannot be used to improve decoding. Therefore, SC and AED have here the same performance. However, if we now use those automorphisms from the lower triangular group, we can construct endomorphisms, which can then be used, as depicted here, to improve the decoding performance over the full SNR regime. Therefore, EED can exploit knowledge of the LTA automorphisms to improve decoding where AED cannot. This brings me to my conclusion. We introduced endomorphisms of linear block codes and derived some structural properties, namely a one-to-one mapping between the set of transformation matrices in a larger linear code, and an algorithm to determine both the transformation matrix and the respective reconstruction matrix. Then we showcased endomorphism ensemble decoding as a possible application, where we also demonstrated or showed a use case where AED can not improve decoding, however EED can. This brings me to the end of my video. If you have any questions, feel free to send me an email or ask in the comments. Thanks for your attention.